All right, well, now it's on to whole program optimization. So we've done our local, we've done our regional, we've done our subroutine. Now it's time to say, well, if we take the thing as a whole, so we've got all of these different subroutines and all of the code that uses them, and we want to compile this into one big final executable, what are the possible optimizations that we can look at? So eventually we'll take a look at two main areas for this. We'll take a look at how we can go through and decide which functions to inline, where we can go through and say, well, instead of actually doing this as a function, let's just take the code from the function and drop it into the place where it's called. And we'll also take a look at subroutine placement. So when we were looking at subroutines, we decided how we were going to organize blocks in the final executable code for that subroutine, or object code for that subroutine. Now we're going to do the same thing with subroutines. Say, well, if we're writing all of our subroutines into an executable, what order should they go in? Again, it doesn't matter from an abstract point of view. They're all going to wind up just being a branch to this and return from here to wherever. So it doesn't matter where they are from a purely abstract point of view, but from a memory performance point of view, it can make a difference. So these are the big things that we want to take a look at as we're going through this. All right, now when we're going through and dividing a program up into subroutines, obviously from a programmer point of view, this is a great idea, right? A software engineering perspective, modularity and top-down design, things make way more sense. We can get a way better design, way better maintainability and all that kind of thing. From a compiler perspective, there are advantages and disadvantages, right? From the compiler perspective, it allows the compiler to go through and compile a subroutine without needing information about the program as a whole, right? Turn that subroutine into object code without needing information about the greater program, which is good. But on the downside, it does mean that we're introducing all this other code that's carrying out the call and return processes, right? That whole division of responsibility, all the things that have to happen to make the call and return work, which adds all sorts of overhead, right? Increases the code size, increases the execution time. So from a compiler perspective, that's not great. And the other thing is, with respect to our optimizations, the idea that we've got this abstraction layer between the subroutine and the place that's calling it means that it's more difficult for the compiler to identify good optimizations across those boundaries, right? It's difficult for the compiler to look at the chunk of code where we're calling something and know if it can optimize that with whatever's inside the subroutine itself. So from some perspectives, a compiler would be much happier if the program, if we didn't use separate compilation, if we just compiled everything together all at once and we had all of the information available when we needed it. So there are goods and bads about this, the whole concept of subroutines from a compiler point of view. But it's not something that's likely to go away, not something that we want to go away. So it's just an obstacle that the compiler developer, compiler writer has to deal with. Now, again, we've got two different aspects of whole program optimization that I want to take a look at here. One of them is the notion of inlining functions. So if I've got some function, here we've got a function f that goes through and computes the sum of the elements in a range of values. So this is actually not the cleverest way to do things, but just so that we've got a function that we can call. And at some point, the caller actually calls the function, passes it a couple of values, and uses the result. It might make sense as far as the compiler is concerned to say, well, maybe this function is only ever called this once, in which case it doesn't make a whole lot of sense to have all of the overhead of the call and return when we could just take this loop and stick it here and compute the actual value here. So again, the notion of inlining is to say, let's replace the function call with the body of the function that does the computation. Now, the trick is that it does have to ensure that, when we lose the function idea, we're losing the scope information that's associated with it. We've got to change the variable names. So now, instead of, if I go through and transform this and stick this while loop at the point of the call instead, then it means that I have to use the caller's names for the values, so I and j, where before I was using a and b. I have to ensure that whatever names I pick for the local variables that we were using inside the function, I have to pick new names for those that are going to be safe, that aren't going to conflict with the namespace for the caller. Again, there have been a lot of situations in the course so far where we've looked at the idea that we need to be able to generate unique variable names anyways. So we'd be going through and generating some kind of a new unused name that's guaranteed not to clash with the rest of the namespace. Here I'm going to use names that are kind of related to the original function and the original function's variable names, just so that it's more obvious where the transformation is taking place. But as far as the compiler is concerned, as long as it generates a unique name that it knows, that's all that it needs. So what we would be doing is replacing this result equals and the call with a block that does the computation, where we're going through and initializing the sum, initializing our index variable, and again using the names from the caller as the variables instead of the names from the original function, and again rewriting the loop using the correct names, and just making sure that wherever we stored the final result for this computation is what we assign to our eventual result here. And nothing terribly complicated other than remembering to watch for our renaming and scoping issues. So this makes a fair amount of sense. Obviously this is going to run a lot faster than the original function call and return, because we don't have all of the overhead of the call and return. It's going to, because we don't have a call and return, we're also not consuming stack space. I guess we are consuming some stack space in that we've got the storage for the local variables here, but we're not passing parameters back and forth. So we've got some improvements in behavior, but if foo, or if our function, this should be f not foo, shouldn't it? If our function was called 1,000 times in the original program, or if it was called from 1,000 different places in our original program, if we did this in all of them, then we'd have this chunk of code repeated 1,000 times in the compiled version of the code. So obviously we're increasing the size of the executable that we're producing. So that is something to consider, is this trade-off between increasing the executable size versus reducing the execution speed, or reducing the execution time. So pros and cons. The other aspect of this is that having done this, there might be better opportunities for optimization across this computation and whatever's happening before and after. Right, so it's possible that the inlined code will produce good local optimization opportunities, right? Stuff that the compiler can recognize and go, oh, wait a minute, I can perform local value renumbering here and see what I can do. Again, we're improving our execution speed at the cost of a larger executable. One of the things that might come up here is if we're doing this a lot, if we're going through and doing a lot of these renaming, then we are generating potentially a lot of these sort of temporary local variable names, increasing the size of the space, and that can become a problem later, especially when it comes to register allocation. So we should come up with some guidelines on when we should and shouldn't go through this inlining process. We'll generally avoid it if there isn't a good reason to inline. We might also consider avoiding inlining if the caller is already really big. If we've got this really big subroutine already, then we might look at that and go, well, do I really want to start doing more inlining and making this thing even bigger? So there are some concerns there in terms of the size of the caller. Some of the things that might cause us to lead towards doing inlining are cases where the callee is really small. If you've got something that's just a couple of instructions long, and to use it, you're going through this long process of the setup for a function call, the function call itself, the return, and the cleanup after the return. It might make way more sense just to replace that little tiny callee with the actual body of the callee rather than making a function call there. So that might be one case where we lean towards inlining. If the call is made really frequently from within a nested loop, for instance, where you'll be replacing it in one spot and yet replacing an awful lot of function calls. So, if you've got a nested loop and in the middle of that you make this call to the function and you inline the function there, then all of those passes through both sets of loops are gaining the benefits of not having the function call and return, and yet you've only got this one point of call where you've increased the size of your code by sort of cutting and pasting the body of the function there. So that's a place where it might make a lot of sense. Again, similar idea here. If the callee is only called from one place or two places or something like that, then you might say, well, I'm not really paying that much of a penalty in terms of code size, because especially if it's only called in one place, I'm essentially just moving the code from the body of the subroutine initially to wherever the call takes place now. So I'm getting the execution speed benefit without really the cost of increasing the executions or the executable size. One place where it might help as well are cases where you're passing constant valued parameters in the function call. So if I'm doing that, then if I replace it with an inline, if I take the body of the function and move it here, then that might provide me with better opportunities to do constant folding with those constant values. Right? I've got my now I've got this little chunk of code that's got more constants scattered in it, and we might come up with a better way to optimize our constant folding around that. So that is another possibility. Similar ideas, if callee is a leaf, again, there are advantages that we can take it. We don't necessarily have to have an activation record on the stack frame, or on the stack rather, for instance, if it's a leaf, so we can take advantages there, and it might make sense to inline. If the callee, actually, I might kind of reverse this and say if a callee doesn't represent a significant amount of the total execution time, is it worth the price of our inlining? So if the callee does represent a significant amount of execution time, that's going to influence yes or no, should we perform our inlining or not. So lots of guidelines, no hard and fast rules here, but again, as you're going through trying to give the compiler some mechanisms for judging when it should and shouldn't inline. Now, all of this relies on the ability of the compiler to go through and analyze these things. To perform these, the compiler's got to be able to figure out if the callee is small enough, or if the callee is called frequently enough, or if the callee is only called from the one place. So we have to gather that information within the compiler before we can use that information. So from a compiler developer point of view, you're going through and saying, well, which pieces of this information can I gather easily during the compilation process and then use to make a judgment call as to whether to inline or not? So all things to consider. All right, let's leave the inlining for a second and take a look instead at the placement idea. Similar to the idea of block placement earlier, where we said, well, if we can organize the blocks within a subroutine in an effective fashion, then when we grab one block, we'll probably grab as well the block that comes after it, or maybe even the one that comes after that too. So we'll get all of these blocks together, and we'll get much better memory performance because all of these things will run together before the next time we need to go grab a new page from memory someplace. So same sort of idea with subroutines. If one subroutine calls another, it would be nice if they wound up on the same memory page so that when we pulled one of them in, we had already pulled in the one it calls. So we want to try and organize our subroutines so that if one function calls another, they're adjacent to one another in memory. So it's going to be pretty difficult if we've got lots of different functions that call lots of different functions. It can be pretty difficult to come up with an organization and arrangement that puts all of the callers and the callees beside each other. Generally what we'll try and do is say, okay, well, if a particular callee calls another one a lot, then we'll try and make sure that those two are close to one another, and we'll go from there. So same sort of idea as previously, where we go through this analysis phase and try and come up with some kind of a mapping of how frequently things call each other, and then try and come up with a layout based on that information. So the analysis phase, we have to build a call graph. So this is just going through and saying, okay, our nodes are our subroutines, and the edges are directed edges that go from the caller to the callee. So we'll get this graph that maps out all of the different calls, all of our different subroutines, and which ones call which. And ideally we'll weight these as well to show how often a caller calls a callee. So how many different edges there are, or the different likelihoods of calls from a caller to a callee. And again, this information could come from estimates from the code base itself, or it could come from profiling information. But again, we want this weighted graph, if you like, with our subroutines and the calls between them. A couple of things to consider as we go through this. We'll ignore recursive calls for this purpose because obviously a subroutine doesn't have to be beside itself in memory, so we ignore recursive calls. And it's entirely likely that there are multiple places in one of our subroutines where it calls a specific other subroutine. Right? There might be 3 places where inside function f where f calls g. So in that case, in our graph, we'd have these 3 different edges from f to g, each with a different weight. So what we'll do to simplify our call graph is to say if there are multiple edges from node A to node B, just add them all together, create them a single edge that's got the combined weight of all of them, so that we get the total count of all the different times that node A calls node B. So we get this call graph created and simplified a bit. And then what we'll do is create a big queue of all of these edges with the highest weights first. So if the most frequent call in here is from node A to node B, then that's the edge that crops up first in our queue. And what we'll do is create a set of placement lists essentially indicating which nodes, which subroutines we want placed near some other. So initially we'll just place each subroutine in a little tiny list by itself, and we'll gradually merge these things together with some kind of order within the lists. So we've got this set of, if we've got 5 subroutines, we've got this set of 5 lists that each have one subroutine in them, and we'll start joining these things together as we go. So while our queue of edges isn't empty, we'll take the kind of the next highest weighted edge from the queue and say, okay, this joins together 2 nodes. So what we'll do is join their 2 placement lists together. So add one to the end of the other and saying, okay, well, we want these things together. So what we need to do then is to say, well, for this edge, we're connecting um, subroutine A, or subroutine X in this case, with subroutine Y, and the frequency W is how often that X calls Y. What we'll do is go through and say, okay, every place in there now where we've got Y calls some Z, we're going to chop Y out of this. So we're going to say, okay, let's have X call Z instead and keep the same weight. And for everything where something calls Y, we'll replace it with something calls X. So each time we pull one edge out, whatever the destination is, we're removing from our graph. Essentially, we're chopping Y out of the graph, and it's essentially because what we're doing is taking Y's placement list and adding it to the end of X's. So Y no longer needs to exist as a separate entity. We're doing Y's stuff through X now. So we go through, we combine X's placement list with Y's. So we've got one fewer placement list, and we've chopped Y out of our graph. And we're just going to keep going through and doing this, grabbing one edge at a time until all we're left with is a single placement list, right? Every single time we do this, we're getting one fewer placement list, and we're merging things together. What we'll wind up with in the end is a list that gives us all of the subroutines in some sequence, and we've pulled these things out from the most used edge to the least. So if the most used thing was X calling Y, then the first thing we'll have here is X and Y. Right? And then we'll go through and say, well, what's the next most used thing? And if it happened to be Y calling A, then what we'll have left in our graph is X calling A. So we'll go through and add A to the end of this list and get rid of A. And that's the sequence this winds up going through. Say, okay, we'll figure out which is the next most used component, merge those things together, and gradually merge the pieces together until we wind up with a single list that says, okay, here's your optimal ordering. We want to make sure that X and Y are together. We want to make sure that A comes after that, and then et cetera, et cetera, et cetera, et cetera, as we go through the list. All right, so if we've got our ideas for inlining, we've got our ideas for laying out the subroutines, when and where shall all this actually happen? Remember that from the compiler perspective, we've got this problem that we're compiling different pieces of the program separately, and then at the end, sometime much later, maybe I compile one file in March, and I compile another one in April, and I compile another one 3 years later, and then 5 years after that, I link them all together into an executable. Well, that means that there are the time when I can do that whole program optimization. At the point where I do that whole program optimization, that's needing information from each of those separate components. Right? So the whole program optimization can't take place when we do the individual compilation, the separate compilation parts. It has to take place at some other point, somehow. So again, this comes back to the idea that from a compiler point of view, doing the separate compilation and then linking is a bad thing with respect to whole program optimization. Right? Whole program optimization is easiest if it's one big file. But that's not the case. That's not going to happen in modern software development. So we have to come up with other ideas. So if you're using some kind of integrated development environment, then as you're going through doing the compilation, right, the development environment is keeping track of the pieces that you're using, and as you link two things together, it's saying, here's a time when we can look at carrying out the optimization on those 2 pieces we're linking together, or those 10 pieces we're linking together. So if your compiler is part of the IDE, then you can have that sort of coordination taking place, where at the point where you actually need it, the IDE can say, now is a good time to do optimization on this combination of things. So that is one possibility. Otherwise, it's entirely likely that if you want to do whole program optimizations, then you're going to have to wait until that link time point where you're actually deciding, okay, now I've got everything, now I'm going to create the executable, now is the time when I can look at my opportunities for performing whole program optimization. Now, in terms of the subroutine layout, where I actually place these things, that makes a fair amount of sense, right? I can go through and decide where I'm going to put these different pieces at link time, because I can do some playing with my memory. Deciding when to inline or not is a bit trickier, because now we're saying, well, if I've got the object code, that's already the result of the compilation of a file that's got a bunch of subroutines in it, then inlining or not has been decided by that point. So either I need to go back to the kind of original code and decide what to inline or not, or have some kind of an indication of where I can take the existing subroutines and inline them now. So anything that hasn't been inlined previously might get inlined now, is one possible way to approach this. But again, it is, the separate compilation aspect does make the whole program optimization a little trickier. What have I done here? Should really have flipped through my slides first. Misordering my slides. So again, this is just a recap of the steps that I was discussing in the algorithm for the analysis side of things. Yeah, I should probably go through and swap the order of those slides. However, again, this is going back and just recapping the placement algorithm, just ensuring that we get the most used function calls grouped together. All right. As strange as an ending that seems like a good place to leave it for now. Again, we've got the basic layers of optimization that we've looked at: the local, the regional, the subroutine, and the whole program side of things. And all of these hinge around the idea of having some kind of good analysis of the data and data movement and structure of the code. And so where we want to go next is getting a deeper analysis of the code base that we're working with. So we'll get into data flow analysis next week and look at how that can be performed, and then a deeper look, if you like, at how that can be used. So that'll be the next stretch we get into.